Welcome back everyone to this already 8th video of this 10-part series on convective wildfires. My name is Tristan Roos, and in the past videos you have been looking together with Brian Verhoeven at how to use weather predictions produced by, for example, the ECWMF or GFS to predict whether or not wildfires result in the formation of pyroclouds. In this video, we will discuss how we can classify the different plumes that we observe in the field. There are plumes that create clouds, but also those that don't. And what does this mean for the fire behavior? In reality, we see a spectrum of plumes, right? We see those that, for example, were similar to the Ponte Vilomara fire in 2022, where there is no cloud formation on top. We also see events such as the Tortosa fire, where a pyrocumulus, a relatively small cloud, developed on top of the plume. And you have the more extreme version of that, for example, during the Santa Coloma de Canal fire in 2021, when we saw the development of a thunderstorm-like cloud, which we call a pyrocumulonimbus. The main difference here, from the plume's perspective, is the height of the lifting condensation level with respect to the plume top. When we have a dry convective fire, the plume is not able to reach the lifting condensation level, inhibiting plume growth. Whereas for the pyrocumulus and pyrocumulonimbus, the plume has been able to successfully reach the lifting condensation level. The main question that we should ask ourselves is, what does this variation in plumes then mean for the fire behavior? And to answer this question, we will first have a look at how we can classify plumes. What is a logical classification that we can follow that covers the whole range of plumes that we see in the field? And then, when we have this classification, let's have a look at how we can connect the classification to fire behavior. Recent research by Marc Castelnau found that we can separate the observed plumes into 5, as he called it, pyroconvective prototypes. He starts with the surface plume, where there's not really any significant vertical motion observed in the plume, and then that can transform into a dry convective plume, meaning there's no cloud formation on top. The opposite of a dry convective plume is, of course, moist convection, which has basically 2 types. You have either a relatively small cloud forming, a pyrocumulus, or a very deep cloud that can reach up to 12 kilometers, which we refer to as a pyrocumulonimbus. The main difference, as I mentioned before, is the level of the lifting condensation level. Because if the lifting condensation level is far above the plume top, we will have dry convection. Whereas with moist convection, we have the opposite, where the plume top is above the lifting condensation level. In the middle between those, we find a scenario where the plume top is around the lifting condensation level. It might be occasionally a bit below and a bit above. So we have kind of a fluctuating ability of the plume to create a cloud. And that is what we call the overshooting pyrocumulus clouds. These overshooting pyrocumulus clouds are relatively short-lasting because they develop once an air parcel accidentally reaches the lifting condensation level, but the cloud is not continuously supported by the plume below it because the plume does not continuously reach the lifting condensation level. So this is basically the middle version between dry convection and moist convection. This summarizes the 5 pyroconvective prototypes. And then the remaining question is, can we couple these prototypes to fire behavior? To couple the different prototypes to the fire behavior, let's take one step back and think about what we know from the impact of convection on fire behavior in general. So let's take, for example, the Ponte Vilomara fire here. And we know from the previous videos that the heating by the fire creates relatively warm air parcels that will rise upwards, creating this vertical rising plume. This convection means that now at the source of the fire, air is moving upwards, which means that we need to replace this air at the surface, meaning that we get an increased inflow into the fire. And this means that the fire experiences a higher wind speed and will move faster in the direction of the wind. But what happens when we add cloud formation on top? For example, during the Tortosa fire in 2024. We again see, of course, that the plume itself is the same convection as in the previous, without the cloud. But now that we have a cloud, and I think Brian mentioned this also in his explanation of the SQTs, is that when you have cloud formation, you have the chemical process where water vapor transforms into liquid water droplets. And during this process, there is a heat release. This is what we refer to as latent heat release of cloud formation, and it heats up the air. And what we know from air that's heated up, it will rise, meaning that the clouds cause additional convection. And if we have additional convection, we will have a stronger increase in upwind inflow and thus a stronger increase in fire spread. So let's move from the theories towards observations. And a very nice plot is this one provided by Mark Castelnau, in which he compares the pyroconvective strength on the upper I-axis compared to the acceleration of the fire spread. And what is really nice is that in this plot you can basically distinguish between the different pyroconvective prototypes that we discussed on in the previous slide. On the lower left corner, we see basically the dry convective plumes and the overshooting pyrocumulonimbus, which have the lowest convective strength combined with the lowest acceleration and fire spread. Whereas if we move upwards, more towards the center of the plot, we find the pyrocumulus events, which have a stronger convective strength, because now we have this addition of latent heat, basically, on top of our convective plume, and that also results into a larger acceleration of the fire spread. And lastly, which makes a lot of sense, is the pyrocumulonimbus, which is in the upper right corner, which have the deepest clouds, so the most latent heat release, meaning the strongest convective strength, combined with thus the largest acceleration and fire spread. And so what we basically see from this plot is that if we move from the smallest acceleration to the largest acceleration, we move from dry convective towards moist convective plumes. And we see that with this change from dry to moist convective, we see an increase in convective strength, which matches an increase in acceleration of the fire spread. And what is interestingly observed but not yet proven is that also when we transition from dry to moist convective plumes is that we see a widening of the fire front. And as mentioned before, this is not yet proven, so I don't have a good theory to support this, but it's an interesting observation because it means that dry convective plumes are generally associated with much more narrow fires, whereas moist convective plumes are generally associated with much wider fire fronts, meaning that moist convective plumes can be generally associated with the largest amounts of burned area. So to summarize our answer to this question that we started with, what does the variation in plume mean for the fire behavior? We first of all can generally classify our observed plumes into 5 pyroconvective prototypes based on the work of Mark Castelnau, which include a surface plume, a dry convective plume, overshooting pyrocumulus, and pyrocumulonimbus plumes. We have seen that pyroconvection generally accelerates the fire spread, but that the presence and the type of clouds do influence the amount of acceleration. Thank you very much for watching, and I hope to see you in the next video.